name is Greg. This is Chemistry News Selection channel. In this channel I select some scientific literature from the areas which I'm interested in, and I show what the authors discovered in their work. I started this channel about a year ago, and all of my videos since then here were in Russian, and now I start to switch to English. This is actually not my first video in English. I had one very short couple of weeks ago. It's made for Veritasium contest. In order to participate, it should get more views. Right now it's about 300. I need probably more than 500. Please click on it. It's only 1 minute video. Of course, also press like to this video if you like it. And today I'm going to talk about a paper from a group of my friend Roman Dobrovetsky and my ex-colleague Boris Tumansky about this paper, which was published recently in Journal of American Chemical Society, which is also known as JACS. Another reason I picked up this paper was because of this comment from one of the guys who checked the article before the publication. Basically what he says is that this work deserves to be in the chemistry textbooks. And believe me, you don't get such reviews very often. So let's see why he thinks so. So the work is about 19-electron molybdenum metalloradical. Molybdenum is a transition metal. Here it is in the periodic table, below chromium and above tungsten. In transition metal chemistry, there is so-called 18-electron rule. This rule says that in the outer shell of a transition metal, there is space for 18 electrons. And why is that? There's 1 s orbital, 3 p orbitals, and 5 d orbitals. Together it's 9. Each orbital can contain 2 electrons, so altogether it's 18. Now, this 18 electron rule is not a very good rule. It's actually a pretty bad rule, although it is useful. It's bad because it not really works. By chemical manipulations, you can make more electrons around metal, or you can make less electron around metal, and it's quite a common situation that this rule just doesn't work. But on the other hand, it's useful because it gives baseline, which you can relate to. So if there is 18 electrons, no problem. You don't really have to explain anything. However, if it's more or less, then you should look for some explanation. That's how the science works. It either try to explain some observations of unusual things, or it actually tries to create those unusual observations by itself, by making things that no one saw before. First, I'll show you an example of how the 18 electron rule works. Example of molybdenum. That's the molecule that we're going to discuss today in some detail. In this case, as I said, molybdenum is here in column number 6. That means it has 6 electrons of its own. There's different ways to count electrons. So neutral molybdenum has 6 electrons on the outer shell. There's one ligand called cyclopentadiene, which comes with 5 electrons. There's 3 carbonyl ligands, each comes with 2 electrons. So altogether here it's already 17 electrons. And one more comes from another molecule exactly the same. So it's a dimer. 2 17 electron complexes, so altogether around each molybdenum we have 18 electrons. And this bond between molybdenums is actually the weakest one in the molecule, so when you irradiate it, this will be the bond that breaks first, and you will get 2 radicals, 2 molybdenum radicals, or in other words, 2 17 electron complexes. It will dimerize because 17 electron molecule is unstable. It doesn't want to exist. It wants to create this bond back to come to its stable 18 electron state. However, there's some ways you can capture this, and that's what people did before. You can take the solution of this compound, and during the irradiation you can freeze it quickly, and in the frozen matrix you can make spectroscopic observations of those radicals. So that's about 17 electrons. Now what about the 19 electrons? So there is basically an idea which people try to do. They try to add another ligand to the irradiated mixture. So for example here this is the phosphine ligand. So this ligand comes with 2 electrons as well. So when the 17 electron molecule form, phosphine can capture one of them and make it 19 electron because it adds 2 electrons. However, if you try to freeze it and observe this 19 electron compound in the matrix, it doesn't work because it's very short-lived. It immediately reacts back with the 17 electron compound by transferring 1 electron and making two 18 electron compounds, which later on react to form the dimer back. So the 19 electron molybdenum compound was never observed. So in this new publication, they came to this problem with more sensitive instruments and with more original ideas. So first, they repeated this reaction of adding a phosphine, and in this case it was 3-phenylphosphine first, just, to understand what they can learn from this reaction. And they actually were very lucky and successful in learning something very interesting. So what did they see? First of all, they checked electron spin resonance spectroscopy. This is the spectroscopy that can observe paramagnetic molecules and radicals, which is 17 electron complex is a radical, is a paramagnetic molecule, has magnetic properties. So this instrument sees this signal. This signal means that there is a paramagnetic molecule in which there is a molybdenum and phosphorus. How we know it? We do a simulation of this spectrum using the observed numbers. If the simulation and the experimental spectrum are so much alike, that proves that we have those two atoms. Another thing that they did mass spectrometry. And in mass spectrometry, you see ions of compounds that exist in this reaction mixture. It doesn't show you the chemical structure, but it again shows you the exact mass, so you can do more intelligent hypothesis of what exact compound can form in the mixture. And this was one of their hypotheses based on this mass and based on this spectrum. They ran quantum mechanical calculations of this compound. They got ESR constants, which are comparable to some extent to the experimental. This considered to be a good correlation of experimental and calculated values. However, still, that's not something that may be worth to spend time on, because it's 17 electron and we look for 19 electron. This compound is, this molybdenum has 18, this molybdenum has 17. There was one very important thing they could learn from this experiment. You can see here that phosphorus has only 2 phenyls. In the original reagent, there was 3 phenyls, so phosphorus lost 1 phenyl. Now, it is not something unusual. A radical has the unpaired electron, which kind of travel over the molecule, breaking bonds. And there were reports before about phosphorus phenyl bond breaking in radicals. That's not something completely unusual. But what it gave the researchers, it gave them an idea that perhaps instead of one of the phenyls, you can put a group which will delocalize the electron and then bring it back to molybdenum. And such ligands are known. However, they were never tried before in this reaction. And they prepared such ligand. This ligand looks like this. Instead of one of the phenyls, they put carborane molecule. Carborane molecule is known for its ability to capture 2 electrons. This bond will become weaker or will break from unpaired electron, but this bond here will survive. So they did the same reaction with this ligand instead of 3-phenylphosphine. And what did they see? Okay, here we have similar spectroscopy, ESR spectroscopy. We see a different picture. Again, simulation perfectly fits the experimental. In mass spectrum, we see the mass that fits this 19 electron compound, which we were hoping to obtain. This fit of the pictures is a pretty good evidence that the assignment is correct. Again, there's quantum mechanical calculations show sufficient identity. But of course, on its own, mass spec and ESR and calculation does not prove the structure. There's additional proofs needed. And those proofs came from chemistry. They basically took this reaction mixture and added so-called trapping agents. They do some reaction with this radical. However, they keep the structure of this radical intact. So I'll explain. So in this case, this ionic compound reacts in a way that it only takes 1 electron from this radical. So it becomes 18 electron complex. In this case, somewhat similar reaction, but with this chloride compounds. Here the chlorine is counteranion and the chlorine bonds more strongly to molybdenum, so it kicks out one of the carbonyls. The idea behind it that those compounds, in contrast to the radical, they could be crystallized, isolated, and their structure was determined by X-ray crystallography, which is the most precise method to identify chemical structure. There's no more precise method than that. And though this evidence, combined with the ESR and the mass spec and the quantum mechanical calculations and the comparison with the 17 electron structure, gives you a very, very strong evidence that you have a long-lived 19 electron radical in this reaction, and this radical lives for about 48 hours half-life. By further changing those ligands, perhaps it can be even isolated in the future. And that's why this reviewer said that this deserved to be in the chemistry textbooks. We have a proof that 19-electron molybdenum compound can exist, something that we didn't know before. But there's more to this reaction. There is actually a very interesting idea here, which was not explicitly mentioned in the paper. Carborane can stabilize compounds under irradiation. What does it tell you? Which other compounds you know that not very stable under irradiation, and if you stabilize them, it can be very useful for the applications in the real life. Perhaps solar batteries. There's no solar battery that lives forever. Maybe paints. You know, there's no paint that not become weaker under sunlight. There's no coatings that's completely not sensitive for irradiation. Maybe some material based on the carborane can be made that if it is added to some structure, some coating, some paint, some solar batteries, it will keep their life much longer. You can try a lot of things. There's applications in biology, in cosmetics, potential of course. I personally hope that some very good things can come out of it. The link to the publication is in the description below. Thank you very much for your attention.